What's up, everybody? Welcome to another video. Hope you're ready to flex those brain muscles. In this video, we're going to practice finding the domain and range of functions given their graphs. We're going to look at 7 different examples. The first 4 are going to be familiar functions like this: linear, quadratic, exponential, rational. The last 3 are just going to be random crazy graphs. Sometimes you're expected to find the domain and range of those, so we'll get plenty of practice in this video. And we're going to focus on 2 notations for domain and range: set builder notation and interval notation. So check with your instructor to see which they prefer, if they have a preference. Here's the first example. Let's jump right into it with a quick review. What is domain? What is range? Here we're given the graph of a function. This graph contains infinitely many points, right? All of the points along this line are points that belong to the function. Each of those points has an x coordinate and a y coordinate. You guys know this. The collection, right? The set of all the x coordinates, that's the domain. Domain is all the x values. The range is the set of all the y values. So for domain, we're looking at x values, we're scanning horizontally. For range, we're looking at y values, we're scanning up and down vertically. Hopefully that's making sense. So for domain, there's 2 different ways we can think about it. Very often, one thing we do is we scan left, we scan right, and we think about, does the function span across the entire x-axis in both directions without having any jumps, holes, or asymptotes? In this case, it does. So we can say the domain is the set of all real numbers. Another thing we often do is we look for like a biggest or smallest x value. This doesn't have one. It goes left and right forever. Another thing we often do is we can think of drawing like vertical lines, right? So we can pick any x value like 2, and we could say, is there a point on this graph with 2 as the x coordinate? Yes, I can go up here. If I go to the right, I can continue to go up. To the left, they're down here. So a lot of different ways we can think about it and identify this. This is the domain, the set of all real numbers. Here's how we can write it in interval notation. It's the entire number line. From negative infinity to positive infinity, we always use parentheses with this. We can't include infinity or negative infinity. These aren't numbers. This just means forever to the left, forever to the right. Or set builder notation. A few different ways to write this. Here's the way I like: x such that x is a real number. So this is like a little C with a line through the middle. Again, the set of real numbers is an R just with like 2 vertical lines like this. It's like a fancy R. What about the range? Now we're scanning all the possible y values up and down. So same kind of thought process. Does it span all the way up and all the way down without having any jumps, holes, or asymptotes? It does. It spans across the entire number line if we look at the y-axis here. So that's one way to think of it. We can also say, well, let's pick any y coordinate, any y value, -2. Is there some point on the graph with that coordinate? Yes. Boom, boom. So this time we're drawing horizontal lines, right? Whereas when we looked at domain, we were drawing vertical lines. We were connecting each of these x values to a point. Now we're connecting y values to a point. I can go up as much as I want. It's going to connect. I can go down as much as I want. All of these are going to connect. So again, we can use the same notation, negative infinity to positive infinity, or the only difference we write here is typically, since it's range, we say y, because range is the set of y values. So y such that y belongs to the set of real numbers. Now, is this always the case when we have linear functions? Do we always have a domain and a range that's the set of all real numbers? For domain, yes. The domain of any linear function is the set of all real numbers. And maybe you're thinking, well, what about a vertical line? That has a domain that's only like one number. That's also not a function, right? Remember, functions pass the vertical line test. So for any linear function, the domain is the set of all real numbers. Every single x value is going to be represented as an x coordinate. Range, this is almost true. There's only one example where the range isn't the set of real numbers, and that's a horizontal line. A horizontal line is a function, and it's technically a linear function. Mx plus b, it's just that m is 0. So a constant function like f of x equals 1 does not have a range of all real numbers. In fact, it has a range that just contains one single element, whatever the constant is. So 1 for that example I gave. So you should be able to pretty easily identify domain and range of the graph of a linear function. Let's look at some other types of functions. Hopefully you recognize this graph. It's a parabola. It's the graph of a quadratic function. We're finding the domain. Remember, we're scanning left and right, all the x coordinates that show up on this graph. And all of them do. It goes left forever, goes right forever. I know my drawing is not the best. It doesn't look like it does, but for any x value I pick, it's going to correspond to some x coordinate. Domain is a set of all real numbers, and this is always the case for quadratic functions. They always have a domain that's the set of all real numbers. Range is where kids often struggle, especially with quadratics that open down like this. And here's why. They're usually pretty good at identifying that 2 is the biggest y coordinate that shows up on this graph. And there is no smallest. The y coordinates go down forever and ever. But think about this. It's two things, I think. It's these arrows that are kind of misleading because it makes us think that like we're going in this direction. And it's also just the way we draw these. If I were to sketch this graph, and even when I graphed this, I started here and I went boom, boom. So we kind of think of this as a starting point, and that leads to this common mistake where students want to do something like this when they're writing it in interval notation, where they want to start with 2 and then go towards something else. The arrows are sort of making them think that. That's not how we do it. Negative infinity is never going to be on the right. When we write something in interval notation, right, the first coordinate is always less than the second coordinate. Negative infinity to infinity, just like a number line. We're going from left to right on a number line. So what's helpful, this is what I recommend to students. Come head on with the graph, boom, head tilt, 90 degrees to the left. Head tilt. If you have a paper, you could just turn the paper instead of tilting your head. But I'm going to tilt my head. Why does this help? Because now the y-axis is a number line in the traditional sense that we're used to. I'm looking at it straight on. To the left are smaller numbers. Down there is negative infinity. Right? To the right are the bigger numbers. And now I can line that up with interval notation where I can see that 2 is the biggest. That's going to be on the right, and it's included. So we're going to use a bracket. And there is no smallest. It goes down forever and ever. So we're going to start with negative infinity and end at 2 since that's the biggest. So in interval notation, the range is from negative infinity to 2. And again, we use a bracket because that y coordinate is included. Okay? Included, use a bracket. Or set builder notation. Here's the general idea of how set builder notation works. We usually say, unless it's the set of all real numbers, we can write it this way. But if there's some restriction, like there is here, we usually say y is a real number such that, and then the condition goes here. What do we need to be true about y? It has to be less than or equal to 2. And that's how it always works. And the condition is usually an inequality or like a not equal sign if we're excluding a number. Boom. Interval notation, set builder notation. So can we generalize about quadratic functions and their graphs? Domain and range. Domain is always a set of all real numbers. Range always has some restriction. If they open down, it's going to be from negative infinity to whatever that biggest y value is. It's the y coordinate of the vertex here, okay? If it opens up, then it's going to be from the y coordinate of the vertex all the way up to infinity, right? So there's always going to be some restriction that involves a bracket. Either there's a biggest y value when it opens down, or there's a smallest y value when it opens up. So this is the graph of an increasing exponential function, and hopefully what you notice is that it spans all the way left and all the way right. Every possible x value is represented as an x coordinate on the graph. So again, domain of all real numbers. Lots of functions always have this domain. There's really only a couple that have restrictions. What about the range? We could do the head tilt. Boom. I'm saying that we're greater than negative 1. For every y value greater than negative 1, that corresponds to some point on the graph. What about at negative 1? This is called a horizontal asymptote. The graph of the function gets closer and closer to negative 1, but it never quite touches it. So we can tilt our head and notice that we're going to start with negative 1 and go all the way to infinity. Negative 1 to infinity. And now we just have to think about what do we put here, and it is a parenthesis because negative 1 is not included in the range. Negative 1 is not represented as a y coordinate. The y coordinates never quite touch negative 1. They get closer and closer. That's this parenthesis idea. So we always use parentheses with asymptotes. Horizontal asymptotes, vertical asymptotes, parenthesis. Or how else can we write this in set builder notation? Y belongs to the set of real numbers such that y is greater than negative 1. That's what this interval means as an inequality. Y is greater than, not greater than or equal to, just greater than negative 1. Boom. Domain, range. Exponential functions always have a domain of all real numbers. The range is usually restricted. You can have decreasing exponential functions as well, where it's from negative infinity all the way up until some number. That is a thing. All right, so this is the graph of what we call a rational function. We can see it as a vertical asymptote. It has a horizontal asymptote. This is a very common look for the graphs of rational functions. Let's talk about the domain, all the possible x values. So I'm drawing like vertical lines. I'm connecting x values to x coordinates that are points on the graph. And I see one issue. When x equals 1, this doesn't connect to any point on the graph of this function. If I go a little bit to the right of 1, it's going to connect somewhere down here. This gets closer and closer to 1, but it never quite touches it. And the same thing if I go a little bit to the left, and obviously anywhere else, this all connects. So really, the domain we could write in set builder notation as the set of all real numbers except for 1. And that's how we can also say the domain in words. The domain of this function is the set of all real numbers except for 1. That's what we call a domain restriction. Interval notation, let's write it out. How do we think about this? Well, all of these x values are included all the way up until getting closer and closer to 1 from the left side here. So we can say this set from negative infinity all the way to 1, but not including 1. And then we could say, well, beyond 1, the same thing happens. Also, from 1 all the way to infinity. Then we connect these with a u. That means union. That means elements from this set, right? Numbers from this interval or from this interval are all collectively the domain. So this means the same thing as this set builder notation, which in words is the set of all real numbers except for 1. This is how we exclude 1. We can think of it as like skipping over it, including everything else. Range, y values, drawing horizontal lines. So we can vertically like this. I'm connecting y values to y coordinates on the graph. I see a similar issue at -2 here. There is no point on the graph of this function with the y coordinate of -2. That should be the only issue, right? I can get really close to -2. We're going to connect if I want to tilt my head here. So how can I write this in set builder notation? Again, sometimes kids find this a little bit easier. Y is a real number such that what? Y does not equal -2. That is our restriction. Now, how can we write this in interval notation? It's going to be a very similar idea. Let's hit the head tilt one more time. Boom, style points. Negative infinity to -2. We're skipping over -2. So negative infinity to -2. We're skipping over -2 and then continuing on to infinity. These are very common ways to write the domain and range of rational functions, which very often have vertical asymptotes and horizontal asymptotes where we need to skip over numbers like this. So I told you I'd give you a few weird examples. Here's one of them. This is a function that just contains 5 isolated points. This is the graph of the function. Let's not overthink this. What's the domain? It's the set of all the x coordinates. Let's go through and identify x coordinates. And since there's only 5 of them, we're going to list them out in a set like this using the same curly bracket that we use for set builder notation. But we're just going to list them out. -3 is an x coordinate. -1 is an x coordinate. 1, 2, and 4. We like to list them in order. If you don't, it's not wrong, but we just like to whenever we can. Boom, that's the domain. There's no way to express this in intervals. We don't have any intervals. Intervals mean from this to this. These are all just isolated points. So this is actually really the only way to express the domain of this function. What about the range? We can do the same thing. Now we're looking at y coordinates. So we can hit the head tilt over here. Boom. We want to go from smallest to biggest, from left to right after tilting our head. -2, 1 shows up twice. What do we do with that? We just list it out once. When we're writing a set like this, we never repeat elements, right? This collection of all the y coordinates, 1 is a y coordinate. We have shown that by writing 1 in here. We don't need to represent how many times it shows up. That's not a thing. For example, we didn't do that with our quadratic, right? Which had some symmetry there and had y values that showed up twice. All right, what else do we got? -2, 1, 2, 3. And that's going to finish off this example. So let's show another one that's a little bit crazier. So this is a good time to check your understanding. Pull out a pencil and paper, identify the domain and range of this function, and write it in your preferred notation. So we're going to go ahead and start. What's the domain? I'm scanning left and right, all of the x coordinates. So what does this hole mean? I wanted to show an example like this with a hole. That means that is not a point on the graph, but everything up to it is. So we can get like as close as we want, and all of those will be points except for that exact point at -2, 1. So -2 is not in the domain of this function, and neither is anything less than -2. We start at -2. If I move to the right, what happens? All of these x values are represented as points forever and ever. So the domain of this function is the interval from -2 to infinity, and I'm not including -2 because there's a hole there. So how can I write this in set builder notation? I could write x as a real number such that x is greater than, not or equal to, just greater than -2. So all the real numbers greater than 2 is how we can say this in words. All right, what about the range? Let's hit the head tilt. Bam. All right, biggest y value I see is 3. There's no hole there. That is an actual y value. So on the right, we're going to have 3 with a bracket. On the left, what are we going to have? Well, this goes down forever and ever. So on the left, we have -infinity. On the right, we have 3 with a bracket. And hopefully that's making some sense. This really isn't that hard. When you tilt the head, once you kind of get the idea of it, get the hang of it, not that bad. So we have y is a real number such that y is what? Less than or equal to 3. Let's write it out and let's do one last example. Boom. All right, so here's the last example. If you didn't get a chance to pause the video last time, pause it now. This is probably the trickiest one we're going to go through in this video. Try to find the domain and range. Write them out in interval notation. Press play to check your work. And just a reminder again, these open circles, those are not points on the graph of this function, but it means that when we have a line here leading to an open circle like this, these are all points. We can get closer and closer, as close as we want, although this exact point is not a point on the graph. Hopefully that's making sense. We have some of those, and then we have some that are filled in as well. Those are points on the graph of this function. So let's find the domain, all the possible x values, and I'm going to show you a cool strategy. I showed this in my other videos when we find domains, so I'll show it here, which was you can take the domain, we can represent it on a number line, and we can use that number line to help us write the domain in interval notation. This is what I often teach students to do. So we're scanning left to right. X values are represented, boom. At -1, there's a jump here, but -1 is represented as an x coordinate of this point. Continue, these are all good, these are all good. Ooh, there's a hole here and a hole here. 1 is our first number that is not an element of the domain. 1 is not an x coordinate of a point on this graph. So here's what we're going to do. We're going to draw an open circle at 1. We're going to say everything less than 1 is good. 1, though, is a problem. 1 is not an x coordinate. We continue. Everything after that should be good. Good after that. So this is the domain represented on a number line, and we can use this to write it in interval notation by saying, oh, we have this union this, right? This corresponds to an interval -infinity to 1 union 1 to infinity. That's this piece here. Hopefully that's making some sense. And again, set builder notation, we have the set of all real numbers except for 1. Awesome. All right, range. This is tricky. We can tilt our head. We can also use this same strategy, which I am going to use. The range on this one is a bit tricky. So let's come over here and tilt our head. I see y values as small as we want, represented. There is an issue here, but don't let this trip you up. You're like, oh, there's a hole here. That y value isn't represented. Well, it is here and here. There's actually 2 points on this graph that have a y coordinate of -1. So just because one of them has a hole doesn't mean that -1 isn't in the range of this function, right? Hopefully that's making some sense. So we can scan up. These are all represented all the way up until 1, but then there's this missing gap here. So let's represent that on a number line. We tilted our head. We said -infinity all the way up until 1, and we included 1. So let's fill in at 1 because 1 is a y coordinate on this function, and everything less than it is part of the range all the way up until 1. And then we jump up to 2, but not including 2. There is no y coordinate of 2 on the graph of this function, right? So not including 2, but then from 2 to 3, and 3 is included. So let's draw that as a filled in circle at 3. So there's a jump here. We're not shading here, but we are shading here. This represents, tilting our head, that piece there. Awesome. Hopefully you're seeing why this is really helpful. Now it's pretty easy to write this in interval notation. I could say, oh, the range is -infinity all the way up to 1, including 1. So the filled in circles correspond to brackets, where these open circles correspond to parentheses. We want to not include 2, but everything greater than 2, but less than or equal to 3. And this is an example where I think it's actually easier to write the range in interval notation than it is in set builder notation. Let's see, how would we write it in set builder notation. Y is a real number such that, let's see, we could say y is less than or equal to 1. That would be this first piece here. And we could say y is also greater than 2. So that's a 2. Sorry, I don't know why it looks like a Z. That's a 2. Is greater than 2 and less than or equal to 3. So we could list out these two conditions. Honestly, I think the interval notation I prefer than the set builder notation for this one. Hopefully this helped. Hopefully these examples helped. Leave any questions you have in the comments below. Any feedback I'm open to. Like, subscribe, do all that stuff to support me. Follow me on TikTok and Instagram. Most importantly, keep flexing those brain muscles. See y'all later. Peace.